Good morning, everyone, and thank you very much for joining us for today's webinar, Advancing Civic Infrastructure, Mississauga Fire Station 123. My name is Shalika Sivathasan, and I am the Administrative Assistant in the Continuing Education Department at the OAA. We will begin today's webinar by acknowledging the land on which we are meeting and calling in from. For millennia, the place we call Ontario has been inhabited by Indigenous peoples and nations who have been stewards of the land and who are deeply connected to its rich cultural and natural landscape. We would like to invite you in a moment of reflection to acknowledge our shared responsibility to address past and present injustices and provide space for Indigenous knowledge and worldviews to shape the architectural landscape of Turtle Island. Before we begin, I would like to share some important information to ensure an effective and professional webinar experience. Please be informed that this session is being recorded for quality and educational purposes. For accessibility, we provide automated closed captioning service available in multiple languages to accommodate the needs of our diverse audience. In order to maintain a stable internet connection, we have muted all participant microphones and disabled video feeds. Kindly note the chat function has also been deactivated. However, we do highly encourage engagement through our Q&A window, which you will find at the bottom of your screen. Feel free to submit any questions that you may have for our speakers there. Questions will be addressed during the designated question and answer period at the end of the presentation. For those seeking continuing education learning hours, please note that attendance is crucial. A minimum of 80% attendance is required for these hours to be accredited to your OAA transcript. Please allow just a few weeks for the processing and reporting of these hours. And lastly, please note that our presenters do not provide insurance, legal, or practice advice, and the OAA does not bear responsibility for errors or omissions in discussions during the webinar. Now, I'm excited to introduce our speakers for today's session. Please welcome Petra Matar, Sebastian Lipczynski, Paul Marcoccia, and John Crozier. Welcome.
Hey, Shalika. Good morning, everyone, and thank you for joining our presentation today, which is titled Advancing Civic Infrastructure, where we will be using Mississauga Fire Station 123 as a case study to demonstrate the learning objectives of this webinar. So today you will be hearing from a few of us who came at this project from different angles. We've got the design team, the capital planning and delivery team, and also the end user perspective. And each of us on this panel have touched the project in a different way as this project came together. But before we get started, we'll do a more in-depth round of introductions and then just dive in. So I'll start by introducing myself. I'm Petra Matar, a principal at DPAI. I was the partner in charge on Fire Station 123, and I led the development of the City of Mississauga's fire hall design standards.
I'm Sebastian Lipczynski, principal at DPAI. I was the project manager on Fire Station 123 and bring an extensive experience delivering fire halls and emergency services facilities.
Good morning, everyone. My name is Paul Marcoccia. I am an architect by background and working as a senior project manager within the capital design and construction section at the City of Mississauga. I spent the first 22 years of my career working in the private practice and have worked in the municipal environment for the last 10 years.
Good morning, I'm John Crozier, Deputy Chief of Capital Assets with Mississauga Fire, and I represent the Mississauga Fire on Station 123 and was closely involved in developing the fire hall design standards that we'll be speaking about today.
Now, before we get into the specifics, it's helpful to step back and look at the bigger picture, namely how civic projects are shaped at the municipal level. That's the perspective that I will be bringing to the presentation today. Advancing civic infrastructure isn't just about designing a building, it's about aligning policy goals, user needs, and architectural response. And the diagram in front of you represents how sustainable outcomes emerge when these forces converge, forming the foundation for clear, repeatable standards that support a consistent and scalable delivery. DPAI led the development of the city's fire station design standards, working closely with both the fire leadership, including John, and our capital design team here at the City of Mississauga to translate operational needs, health and safety priorities, and long-term municipal goals into a consistent design framework that can be applied across multiple stations. And with the volume of new and renovations renovated stations currently being delivered for Mississauga Fire and Emergency Services, or MFES. There's real value in having standards and templates that any design consultant can pick up and apply consistently. It provides a real great continuity across all of our projects. And at the same time, this framework allows flexibility for the different scenarios we face on sites, whether that's a 2-truck or 3-truck station, a single-story or 2-story station, so we can respond to site-specific constraints while we still meet operational requirements for each of these unique projects.
And building on that, from an operational perspective, the template gives us structure and clarity. It clearly defines fire's requirements in a way that's scalable, repeatable, and applicable across both new builds and renovations. Currently, we have 6 new stations and 17 major renovations that will be referencing in this document. So it's not just theoretical, it's actively shaping how we are delivering these projects. It ensures that every consultant and every project manager is working from the same set of expectation. And it keeps design decisions aligned with operational priorities, not personal preference. Without that framework, every project will be like starting from scratch. We'd see inconsistent interpretations and applications, lessons learned not being applied and carried forward, and a significant amount of time spent reestablishing just the most basic requirements.
So to bring this into something tangible, we are going to use Fire Station 123 as a case study. And Sebastian, who was the project architect on 123, took the standards that Paul and John talked about and applied it onto a real life project. Working closely with the city's capital design and construction team and the Mississauga Fire and Emergency Services, including John, he led the application of those principles in real time.
So this location wasn't random. It was specifically identified through our Mississauga Fire Master Plan, which called for 6 new stations to support city growth and to address our declining emergency response times. Fire's goal is to respond to emergencies within 4 minutes, 75% of the time. The most effective way for fire to improve the response times, which is travel times, is the strategic placement of new fire stations. This particular area has a higher risk residential occupancies and a high call volume where response times are below target. So this site directly addresses that gap. It also houses our technical rescue teams with quick access to the QEW, the 403 and the 407. This location's ideal. And because it's an established residential community, we engaged early and consistently with local residents, making sure that they understood the benefit of having a fire station in their neighborhood, which was key to gaining their support. Everybody wants a fire station close by, but very few want them in their backyard.
I'm going to pause because we got a question from one of the attendees saying there is reverberation with double voice at the same time. And I'm not sure if this is for everybody or just for this individual, but we will continue. But if anybody else has that issue, please post the question.
So just like any other site, there were several key site constraints that really shaped how the building was developed. We were dealing with a 3-meter front yard easement with Electra, which was fully integrated into the overall site planning and building placement. Required setbacks from the G1 Greenlands. Zone influenced the driveway geometry and circulation within the site, ultimately requiring a minor variance application within the city. The site layout was carefully developed to support safe and efficient fire apparatus movements in and out of the bays, with truck parking provided at both front and back of the station. The building massing and orientation were optimized to maximize solar exposure to primary occupied spaces, while lower roof areas were strategically positioned to optimize the solar PV installation. The irregular site geometry and constrained property width drove a highly optimized building form. The site circulation also needed to accommodate the residential size Peel region waste collection requirements so that the trucks can be able to turn around at the back and leave the site. Hydro servicing constrained us by having Electra require a single approved vault location at the front, requiring a tight coordination with the site layout. Lastly, our emergency generator was deliberately located away from the westerly residential neighborhoods to mitigate potential noise and operational impacts. So all of these constraints and operational drivers really shape the final form you see here. The building is really a direct response to its context, the residential edges to the west, major road access to the north, and operational needs that are embedded within the layout.
So this is likely what brought most of you here, the learning objectives, or maybe it's the climate action hours. We won't judge. But either way, we've structured this presentation around these 4 themes. As we mentioned, we're going to be using Fire Station 123 to explain each one of those learning objectives. But before we dive in, I want to get a quick sense of who's on this webinar today. Shalika is going to launch a short poll to understand how familiar you are with the design of fire stations, and we listed it as 4 categories. Not familiar, which means you've never worked on a fire station; somewhat familiar, you've studied or reviewed fire station projects; fairly familiar, you've worked on 1 or more fire stations; and extremely familiar, you specialize in fire station design. And once we receive, I think 70% of the votes, we'll get a better sense and move on. Okay, so the majority of the attendees are not familiar with fire station design, which is great because we have structured it with that assumption. So let's get into the first learning objective. And the first one is identifying key design principles that ensure durability and operational resilience in fire halls operating 24/7.
From an operational standpoint, the building's a tool. Mississauga Fire's focus is responding to emergencies, and that's what firefighters take pride in. That's what they care about most. The facility has to support that. It cannot get in the way, and it cannot demand too much attention. These buildings operate 24 hours a day. While we aim to design energy-efficient buildings and avoid oversizing our mechanical systems, the apparatus bay is fundamentally different from any other spaces in the station. The apparatus bay's doors open and close in every season, in all weather conditions, often without warning multiple times a day, and often in the extreme cold. As an example, in the winter, you can have both bay doors open and both fire trucks exit the apparatus bay to respond to a call. They could be gone for 10 minutes or several hours. When they return, they can often come back covered in snow, ice, frozen, with dirty tools, equipment, and gear. The apparatus bay needs to recover quickly, restoring heat, dry and warm the apparatus, support the firefighters cleaning of their tools and equipment to be ready for the next call, which could be minutes away. Any one of our 33 crews could be assigned to this station at any time. Building systems, control, and processes need to be intuitive to be effective and adopted. Firefighters are focused on emergency response, not learning building controls.
From the city's side, we're always looking at these buildings as long-term assets. We're maintaining them for decades, so durability is not just a design decision, it's a life cycle decision. We work closely with MFES to make sure that the finishes and assemblies can truly handle 24/7 year-round use. We're thinking about impact, cleaning, wear and tear, and long-term replacement cycles. The goal is to deliver a high-performing asset for the city over its full service life, not just something that looks good on opening day. At the same time, it's a civic building. It has to represent the city well, so there's always a balance between toughness and appearance. Ultimately, we want to give MFES a building that serves them well every single day, supports their operations, and holds up over time without becoming a maintenance burden.
One of the most critical exterior decisions for the station was the apparatus aprons. These trucks are extremely heavy, and the bays see constant starts, stops, and turning movements. In the summer conditions, especially asphalt can rut and deform under that kind of load. So we used reinforced concrete in the highest stress zones to provide long-term stability and reduce surface failure at the bay thresholds. We also carefully detail the transitions between the interior slab and the exterior apron to manage movement, drainage, and repeated impact. It seems simple, but this is one of the hardest working areas of the building. Getting it right protects the envelope, maintains safe access for the apparatus, and reduces long-term maintenance. Inside the station, the same durability mindset continues. Our high traffic areas, we ended up using large format tile which allows us to have fewer grout lines, meaning easier cleaning, fewer places for contaminants to collect, and better long-term performance under constant use. Concrete block walls were used in areas prone to impact or heavy activity. They hold better up over time and reduce repair cycles. We also specified solid surface windowsills instead of laminate for improved moisture resistance and cleanability. These are small decisions individually, but collectively they support a building that operates continuously. Going further into more programmed areas within the building, we selected wood look ceramic tile to introduce warmth and more residential character, while still performing like a tile under constant use. In the kitchen and across the project, solid surface countertops and high impact laminate millwork were chosen to handle frequent cleaning and daily wear without breaking down. The goal was really to create spaces that feel supportive for the crew, but are still built for continuous operation.
And from the city's perspective, selecting these higher durability materials often comes with a higher upfront cost. But that investment is offset over time through reduced replacement cycles and lower maintenance demands. And equally important for us is the more robust materials mean fewer disruptions to operations, fewer needs to replace materials. And in an emergency facility, maintaining this type of disruption is critical.
So not only do finishes and materials matter, the layout of the station is just as critical. Our goal is to save lives, protect property, and protect the environment. And in that context, every second counts. Fires can double in size in every 60 seconds. On medical calls, the chances of a successful resuscitation drop about 10% for every minute of delay. Once a call comes in through the in-station alerting system, crews have approximately 60 to 80 seconds to get their truck out of the bay and roughly 4 minutes to reach the scene. The building has to support that reality. There can be no unnecessary turns, no dead ends, clear and direct circulation from the living areas to the apparatus bay, wherever you are in the station, so that a quick exit is possible. Fire Station 123 does this very well. The adjacencies and travel paths were very deliberate, and that directly supports and enhances our response performance.
And that's a great example of the kind of first principle relationships that the design template standards are designed to protect. It ensures thoughtful circulation and response efficiency are embedded into each and every project.
So what does that look like in practice in terms of the circulation? So the images here show the main circulation paths from the living areas directly to the apparatus base. This is the primary response route. It's clear, direct, and intentionally kept free of any obstructions. Sight lines are maintained forward, so there's no hesitation about where to go. The fire call printer is recessed to keep the corridors clear, and built-in millwork discourages any furniture from creeping into the path over time. There's also direct access from the captain's offices and from the bay itself, keeping movement fluid during any call. It's simple, but deliberate, clarity, speed, and no obstacles. So looking beyond layout and finishes, resilience is embedded into the building systems. The HVAC strategy uses clear zoning to so different parts of the station can operate independently and respond to varying occupancy and use patterns. The apparatus bay uses a radiant floor heating system, which supports rapid temperature recovery after winter deployments, helping stabilize the space when trucks return cold. Mechanical equipment was selected specifically for durability under continuous operation, and the building automation system allows facility staff to monitor performance, anticipate issues, and plan maintenance proactively.
From the city's perspective, every new fire station is designed to operate independently during a power outage. Each facility is equipped with a full building standby generator, to maintain uninterrupted emergency service. We also prioritize a high-performance envelope design, which helps maintain interior conditions longer during any utility disruptions. And these investments really do ensure that the station remains functional when the community depends on it most.
So far we've talked about durability, speed of response, and system resilience. But just as critical is protecting firefighter health, which brings us to zoning and design strategies that prevent cross-contamination and support long-term wellness. But before we get into zoning in more detail, knowing that 60% of the people on the webinar are not familiar with fire station design, it helps to start looking at, let's look at the layout of a fire station. So there are two primary parts. Essentially, there is the apparatus bays and the living areas for a fire station. The apparatus bays are the operational heart of the building. They sit at the center and everything is organized around them to support quick, efficient response, like John mentioned. On one side of the bays are the crew living spaces. Within that side, there's a clear gradient designed into the station from limited public access to fully private crew areas. So near the main entrance, you'll typically find spaces like the captain's office and the gym, allowing controlled public access without bringing visitors into the operational core. And then as you move deeper into the crew side, the spaces become increasingly private. Dorms and washrooms and change rooms are positioned adjacent to the bays, with shared spaces like day room, kitchen, and lounge located further into the station where firefighters spend most of their time between calls. Now, on the opposite side of the bays, away from the living areas, are the operational support spaces. This includes the gear wash, bunker gear storage, the SCBA room, and equipment areas. Keeping these functions consolidated and separate from the living side supports efficiency and helps manage contamination control. So overall, the layout is very intentional. Bays are at the center, living on one side with clear public to private gradient and operational support on the other. All of these are working together to balance speed, safety, and daily crew life. So that was the broad programmatic organization. But when we began developing the standards, a critical point rose to the top in every conversation we had with fire leadership, which is contamination and how easily it can move through a station. This is not an abstract design problem. It's a critical operational health concern. So conversations that we had were centered around where does the contamination originate? How does it travel? How do we prevent it from reaching living spaces or even going home with firefighters? And that shifted our focus from simply organizing rooms to also mapping movement of people, gear, air, and exhaust. So we walked through the return from call sequence in detail, where gear is dropped, where decontamination occurs, and at what point a space becomes clean again. And the diagram that we came up with that you see on the screen represents that thinking at a very high level. And it became the foundation for how zoning was formalized in the template design.
And from the fire perspective, this isn't just theory. Firefighters face a significantly higher cancer risk due to their occupational exposures. We have to do better at protecting our crews. Clear zoning is a major part of that. Designated hot and cold areas, dedicated and ventilated bunker gear rooms where off-gassing can occur safely, and purpose-built laundry and decontamination spaces. Even small design details have real health implications. Simple things like hard, cleanable surfaces that do not trap contaminants, and separate clean and dirty janitor's closets to prevent cross-contamination. The objective is straightforward: a clear, efficient path that moves people and equipment from contaminated to clean without having to cross back.
So this slide and the next few show how the zoning strategy is applied spatially at Fire Station 123. And I will let John walk through these zones in more detail.
So we treat the apparatus bays, gear storage, maintenance areas, and laundry in what we refer to as a hot zone, spaces where contaminants are assumed to be present. This is the first zone the crews enter when returning from a call. The apparatus is parked and exhaust is immediately captured from the truck. From there, trucks, tools, equipment, hoses, and many other things are removed from the apparatus and contaminants are cleaned off of the equipment from what was picked up at a scene. Gear and PPE move through dedicated decontamination and laundry spaces, where equipment like gear extractors, gear dryers, mechanical cleaning take place before they're stored back into a ventilated bunker gear room or on the apparatus. The goal is simple: to contain contaminants at the source before they can migrate deeper into the station. The living, sleeping, administrative, and kitchen areas all make up the cold zone. These are spaces where firefighters spend most of their time between the calls, eating, sleeping, training, studying, or handling day-to-day work. It's what we call the living quarters or living side of the station. Because this is where crews rest and recover, it needs to function more like a healthy workspace or like a home environment than an industrial space. That's why protecting these areas through circulation, separation, and building systems is so important to the overall design. Another critical part of the layout is how we manage movement between these zones. The transition from the apparatus bay into the rest of the station follows a very clear and deliberate path. These points are controlled through strategic door placement, clear and consistent signage, and the pressure relationship within the mechanical systems. They function almost like checkpoints, guiding crews through the proper decontamination sequence before entering the clean areas. It's not relying on a single strategy. The planning, physical separation, and mechanical systems all work together to prevent contaminants from migrating into living spaces. It's easy for firefighters to do the right thing when they don't have a choice and they don't have to think about it.
So here you can see how that separation shows up physically inside the building. This is the dirty side janitor's closet, along with the signage clearly identifying the clean zone beyond. Material change, door placement, and signage really make the boundary obvious. So there's no ambiguity about where contaminated equipment should really stop. So the architecture really enforces this process. So this is what a return from a call decontamination sequence looks like. Crews come back into the apparatus bay and move directly into the dedicated gear decontamination area. Gear is then cleaned and stored in a ventilated bunker gear room, completely separate from the building side of the station and supported by its own recirculation system. At the same time, the firefighters move through the showers and personal decontamination before entering into the cold zone. The key takeaway is that the gear decontamination happens away from the living areas with dedicated ventilation and separation built in already. It's a straightforward progression from dirty to clean with no shortcuts, designed to keep contaminants contained on the operational side of the building.
This sequence is fundamental to our cancer prevention efforts, and that's why you hear us talk about it so much. This transition from dirty to clean has to be efficient and effective, and it has to prevent crossover back into the clean areas. That expectation is clearly built into the standards, so every project team understands it from the start. From there, each station refines the sequence architecturally, depending on the site, layout, and apparatus configuration, but the core principles remain the same.
So we've talked about zoning in physical terms, which is walls, circulation paths, control transitions, signage, etc. But contamination control does not stop at the physical and spatial separation. It has to be reinforced through the mechanical systems. That's why the station has to be organized into distinct pressure zones to help contain exhaust and airborne contaminants from traveling. The apparatus bays operate under negative pressure, while the living quarters and support areas are maintained under positive pressure. This pressure differential is intentional. Air moves from clean spaces towards contaminated zones and not the other way around. So each zone is also served by a separate HVAC system. This way, air isn't being recirculated between the dirty and clean areas. Furthermore, where gear is stored has its own separate recirculation system to further contain gear off-gassing into the rest of the station. So the architecture and the HVAC are working hand in hand. The architecture defines the zones, but the HVAC systems support it further. And moving on from the operational performance and occupational health, the next objective tackles how fire station design can support gender diversity and equity through the planning of accommodations, washrooms, and shared spaces.
Fire service has changed significantly over time. The workforce today is much more diverse than ever. In 2003, there were just 8 female firefighters. Today, we have well over 60, and that number is growing. Participation of women in firefighting, along with greater racial and cultural diversity, has steadily increased over the past decade, and that trend continues. Stations need to support all firefighters, regardless of gender identity, sexual orientation, race, culture, or religion. With that shift comes a clear expectation of privacy, dignity, personal safety, and accommodating personal preferences or needs. Design can either create barriers or remove them. Facilities should support the crew dynamics as they are today, not how stations were designed decades ago. This approach allows stations to adapt to changing staff ratios over time, which supports recruitment, retention, and future workforce diversity without major renovation.
So building on that shift in workforce, the standards intentionally move away from traditional gender segregated washrooms and showers and instead embrace a more adaptable approach. So rather than designing for fixed gender assignments, aka male and female washrooms, we prioritize standalone gender neutral washrooms and shower rooms. Each space is fully enclosed, providing privacy and dignity for every firefighter. This approach supports diverse crews without requiring special accommodations or operational workarounds. In the locker area, standalone change rooms are also included for added privacy. The result is a flexible, future-ready model that supports inclusion while remaining simple and operationally efficient. On the left is a fire station built in 2002. So at the time, the design was already beginning to respond to the increase in women's participation in fire services, even before the formal standards were established. But still, the framework was creating those separate, gender segregated washrooms. Whereas on the right is the plan for the Fire Station 123, where those lessons have been formalized through the standards into a more adaptable and inclusive layout for showers, washrooms, and locker areas. And that same adaptable design principle that we applied to the washrooms also informed how we approached dorm layouts. The standards move away from the large shared bunk rooms that we used to traditionally see towards semi-private or individual sleeping zones. Each firefighter has a clearly defined personal area for rest and recovery, with visual and acoustic separation built into the layout. The planning also includes a space for a small desk or study area, recognizing that firefighters use these spaces for more than just sleeping. The original standard introduced lower partition walls as a pragmatic step forward from historic open dorms. But at Fire Station 123, Sebastian really pushed those partitions up even higher to further improve this privacy that we're trying to achieve. So the result is a flexible model that supports equity and operational adaptability without requiring gender-based dorm assignments.
And to help put that into perspective, this is what a typical dorm looks like in many of our older stations. It functions as a dorm, a locker room, sometimes a gym, even a training or studying space, all in one open area. There is no privacy. The space was forced to serve too many functions at once. The workforce and expectations have changed. The area of a large open floor dorm with no privacy is fading. Firefighters work very different schedules and have different rest cycles. They have unique habits or customs and have very different recovery needs between calls. The semi-private dorm model strikes a balance. It provides privacy without isolation and maintains safety and visibility while moving away from open bay dorm areas.
And this sequence of images shows the difference between the old dorms and the new ones. So what you see in the first image is looking into the dorm area, and to the left and to the right of that corridor are the individual sleeping rooms, which include for the bed and the desk. There is a 6-foot wall between the sleeping area, so there's still connection, but there is high levels of privacy. Instead of fixed doors into the sleeping areas, what we have provided for are curtains. So when they are open, this is an invitation to create a more open space, but when they are closed, firefighters have the option to have a more private space. So inclusion for the crew is one layer, but accessibility to the public is another important responsibility of these buildings. In the diagram we saw earlier that defined the hot and cold zones, areas requiring barrier-free access are also identified with a blue border. So why would we need accessibility within a fire station? Because they are considered post-disaster buildings, and they must function as barrier-free spaces for emergency public use. Public entrances require a continuous accessible path of travel into the building. That includes access to community-facing spaces like the gym, and where appropriate, the apparatus bays. Captain's offices and meeting spaces must also be accessible, whether for visitors, administration, or injured staff. A universal washroom is required by code, and it must meet accessibility standards. These requirements are particularly important because stations not only serve the crews, but they also regularly host school tours, community visits, and other public-facing functions. So these spaces need to be accessible and easy to navigate. And important to know that operational only spaces such as the dorms, fitness rooms, host towers, and upper floors, or even like basement storage, are exempt from barrier-free requirements. Now, when we move into the shared spaces, the kitchens, lounges, and work areas, these are designed to balance privacy, noise control, and communal life, supporting mental well-being and team cohesion in a 24-hour environment. And as you can imagine, being in a work environment that's 24 hours, that will require an additional level of care. So the crew is often using these spaces simultaneously, sometimes as a group, sometimes individually, depending on preferences and the needs. And the layout has to support both connection and a variety of activities without conflict. Each space is designed to flex, so the dining room can easily function as a meeting or training space. The lounge furniture can be moved aside to accommodate drills or larger gatherings. The dining area opens directly to the kitchen to maintain connection, and workstations are located nearby so daily tasks remain integrated into this shared environment. The intent is to create spaces that adapt throughout the day, supporting training, collaboration, downtime, and everyday living within the same footprint.
These shared spaces play a real role in supporting and improving mental health. Large lounges and dining tables aren't just about meals. They are where crews debrief, they connect, and protest what's just happened on a call. Some conversations are formal and some are not. After a particularly difficult call, firefighters don't all respond the same way. Some need to talk it through with the group, others need a moment to step away and decompress. The station has to support both. These rooms also accommodate training, including live virtual sessions broadcast to stations, which may be a classroom style delivery or practical hands-on sessions. So these spaces have to transition easily without disrupting others. Over long shifts, that flexibility matters. These environments help crews recover, stay connected, and be ready for the next call.
So our learning objective number 4 shifts us to sustainability and how the fire station can act as a civic exemplar. We'll look at the energy performance, low carbon material strategies, and resilient site planning that position these buildings not just as an emergency infrastructure, but as a climate forward public asset. Of course, these sustainability strategies aren't So these sustainability strategies aren't happening in isolation. They're guided by the city's broader climate commitments and performance standards. And I'll hand it over to Paul to speak on how these strategies are grounded in the city's broader sustainability mandate.
Thank you, Sebastian. From the city's perspective, sustainability is grounded in formal policy and long-term climate commitments. In 2019, Council declared a climate emergency, which led to the development of the Climate Change Action Plan and the Corporate Green Building Standard, or CGBS, as we'll refer to it. The CGBS establishes clear environmental performance requirements for new municipal buildings, with level 3 representing the highest tier of performance. That was the initial target for Fire Station 123. The implementation of the CGBS has been a significant shift in how we approach major capital projects. It doesn't just apply to specific buildings. It has influenced the broader mindset across all of city work. A newer version of this standard is scheduled for release in 2026, and this will continue to raise the expectations for performance and accountability. Because fire stations are highly visible, community-focused buildings, the intent has been to push performance, ultimately targeting net zero energy. The pathway to net zero energy is straightforward in concept. First, you minimize the energy demand, and second, you maximize on-site renewable generation. So on the energy demand side, that starts with a high-performance envelope. So we utilized R25 walls, R40 roof, triple glazed sealed units, and high-performance apparatus doors. It's also supported by a high-efficiency all-electrical mechanical system, including VRF heat pumps, electric slab heating, and heat pump water heaters. When you reduce energy demand significantly, solar then becomes viable as the second step in the equation. So at our recently completed Fire Station 125, which was the city's first net zero station, modeling shows an approximate 85% reduction in greenhouse gas emissions compared to a typical fire station. This work directly supports the city's 5 strategic pillars for change, specifically the green pillar within the strategic plan. And these buildings aren't just infrastructure, they're aligned with our highest level policy goals.
From the perspective of fire, the transition to an all-electric or net zero station can't come at the expense of operations. Stations run 24/7. There's no downtime, there's no off-peak period, and there's no tolerance for reduced performance. The building has to fully support emergency response at all times. Crew comfort, contamination control, reliability are all baseline requirements, not enhancements. Buy-in from the crews come through demonstrated performance, not just theory. If it works operationally, they'll support it. The systems need to be reliable, simple to operate, and capable of handling continuous use. If they're overly complex or prone to failure, that directly impacts operations. And honestly, if firefighters never know that the station is net zero, then that means we've done something right.
As Fire Station 123 is a new build, the mandate for this build was to meet Level 3 energy performance under the CGBS. Level 3 is the highest performance tier for fire halls within the CGBS, with strict targets for energy use, thermal energy demand, and greenhouse gas intensity. These targets go well beyond code minimum, and require an integrated design approach. So achieving Level 3 meant that the envelope, mechanical systems, electrification strategy, and on-site renewables had to function as one coordinated system.
And before we look at the sustainability features of the project, it helps to understand what these metrics actually measure. Starting with energy use intensity, this is the total energy use per square meter. So think of it as overall building efficiency. TEDI, which is the thermal energy demand intensity, measures how much heating energy that building envelope requires to maintain indoor temperatures. So this one is envelope driven. And GHGI, which is the greenhouse gas intensity, measures operational carbon emissions per square meter. This reflects fuel choices, gas versus electric. So what does it mean to move from level 1 to level 2 to level 3? What are we really looking at over here? From level 1 to level 2, the EUI is a 24% improvement. And then from level 2 to level 3, that's another 25% jump. So there's almost a 43% jump between level 1 and level 3. TEDI, between level 1 and level 2, is a 20% improvement, but the real jump happens from level 2 to level 3, which is a 50% improvement. And for greenhouse gas intensity, the big jump is happening between level 1 and level 2, and no real jump between level 2 and level 3. So what does that all mean? Moving from level 1 to level 2 is largely about a carbon shift. So fuel switching and electrification really start to play a major role from level 1 to level 2. But that jump from level 2 to level 3 is different. That's where the envelope performance becomes critical, particularly the deep reduction TEDI. And when you look at the numbers, that's where the real lift is happening. So for a 24 fire station with large apparatus bays, high ventilation rates, and frequent doors opening, a 50 to 60% reduction in TEDI is very, very significant. That level of reduction requires strong air tightness targets, a thermal bridge-free detailing, high-performance glazing, and optimized heat recovery systems. So this is not a single move. It's an envelope-first design working in coordination with mechanical systems. So level 3 essentially is pushing that building toward the all-electric performance supported by a high-performance envelope, which Sebastian is going to go further into.
Thanks, Petra. So hitting this level 3 requirement is really one thing. Delivering it with a municipal budget is a completely other ballgame here. When we talk about delivering a net zero energy fire station within budget, it's important to understand the sequence behind it. So delivering a net zero wasn't achieved by just layering on more equipment. It came from making disciplined decisions in the right order. We started with the building envelope by strengthening insulation, improving air tightness, upgrading glazing, and paying very close attention to the thermal detailing, we reduced energy demand. We can reduce energy demand at the source. And that's the most cost-effective move you can make, because every unit of energy you don't need in infrastructure, you don't have to build. With the reduced load, we were able to right-size the mechanical electrical systems. Smaller systems, properly calibrated to the actual demand, are not only more efficient, they're more economical to construct and operate over the life of the building. Only after we've optimized the demand did we layer in renewables like rooftop solar to offset the remaining energy use. That ensured that we weren't overspending on generation to compensate for inefficiencies that we could have solved through design. So throughout the process, energy modeling and life cycle analysis guided our decisions. It wasn't guesswork, it was a measured and iterative process. The result is a station that meets net zero energy targets while maintaining budget discipline and ultimately delivers a resilient long-term municipal asset rather than a short-term performance statement. So as we moved from a high-level strategy into implementation, budget discipline became even more critical, especially on the mechanical and electrical side in a fully electric net zero energy facility. In a typical fire station building, the M&E systems might represent around a 16% of construction budget. On Station 123, that number had to increase to roughly 24% due to this electrification and renewable energy integration. With an overall cost over $1,000 a square foot, managing that escalation wasn't an option, it was essential. What made the difference was how closely material and envelope decisions were tied to the mechanical strategy. By tightening the envelope, improving insulation levels, optimizing window performance, and being intentional about our electrical loads, we're able to reduce the overall demand on the building. That reduction directly limited the scale and cost of the systems required. At the same time, materials weren't selected on first cost alone. They were evaluated through a life cycle lens, considering durability, energy performance, and long-term operational impact. That alignment between envelope, material, and M&E systems is what ultimately allowed the project to meet the city's energy objectives without losing control of the budget. So as we were starting with our envelope strategies, we had reviewed multiple structural wall systems options to ensure design had met performance goals while staying within that allocated budget. Each option that you're seeing here on the screen was evaluated for their thermal performance, embodied carbon, and constructability, life cycle durability, and cost impact. We weighted the pros and cons carefully, balancing sustainability objectives with financial constraints. That the selected envelope not only aligned with the established budget, but also met the project's energy performance requirements in coordination with the M&E systems, which were validated through our energy modeling process. So at the core of our performance strategy is a continuous high-performance thermal envelope. We approach the building as one complete thermal system, not a collection of parts. So that resulted in an effective R60 for the roof, an R40 for the walls, R15 below the whole slab, and R30 at our foundations. That had established a very strong baseline before we even began talking about mechanical systems. Just as important as the insulation values themselves is the detailing, transitions between the assemblies were carefully coordinated to maintain continuity and limit any thermal bridging. That goal was consistent, no weak points. Because we were building in climate zone 5, we were able to benchmark everything against the building code. The roof assembly performs approximately 70% better than code. Our wall systems are about 135% better. Foundation walls were roughly 100% greater than our value required in code. And the slab on grade insulation exceeds approximately 540% as it's the full slab as opposed to the 4 feet around the perimeter. So this is incremental improvement. It's a deliberate step in changing the building's performance. That thermal foundation is what allowed the mechanical systems to be optimized and the net zero target to remain achievable. So from a construction sequencing, we prioritized the envelope continuity. Rigid insulation was installed continuously at the foundation walls on both sides of the walls and beneath the entire slab footprint, as you can see here in these photos. Detailing at the footings, slab edges, and wall transitions ensured long-term thermal performance in a high-use 24/7 facility. This approach reduced the risk of condensation, improved interior comfort, and reduced the durability, enhances the durability under operational conditions typical of fire station buildings. At the superstructure interface that we're seeing here in these photos, masonry was supported using thermally broken shelf angles, which are the ferro brackets. This allowed the exterior insulation to remain continuous from the foundation wall right through and behind the bracket, allowing the building envelope without interruption, eliminating a common source of our thermal bridging at floor lines. An added benefit using the ferro bracket is that it had reduced the need for larger masonry bearing ledges at the foundations. By transferring these loads more effectively, we were able to minimize foundation projections and overall concrete volume. This not only improved the thermal continuity, but also reduced the material use and associated embodied carpet. The insulated zip sheeting is used at the exterior wall assemblies to provide a continuous thermal air barrier between the exterior environment and our cold form steel metal studs and structural steel framing. This improves air tightness, reduces thermal bridging through the steel structure, and enhances the long-term envelope performance. Now, working our way from exterior into the inside and the mechanical plant, we designed the building around the air source heat pumps connected to a VRF fan coil system. This gave us the efficiency through electric heating and cooling, with the flexibility required in a 24/7 facility. Our VRF system allowed us to zone the station, living quarters, the offices, training, and support areas, so that each of those zones respond to how it's actually being used. That improved the comfort for the crews while avoiding unnecessary conditioning in low occupancy areas. Because it's decentralized, we're not only relying on a single piece of equipment to serve the entire building, which supports operational resilience. For ventilation, it was handled through the energy recovery ventilator, which recovered heat from the exhaust air and transferred it into the incoming fresh air. That significantly reduced the energy required to condition outside air, especially during the winter operation. In the apparatus bays, heating is provided primarily in the inflow radiant heat, delivering steady, durable warmth in large, high-volume space. Unit heaters are then located at each bay door and controlled by localized sensors to activate only when the temperatures drop, typically when the doors open in the winter, allowing for a targeted recovery without running continuously. Importantly, all of these systems are integrated into the building automation system and are monitored by the city's building management team. This allows for real-time oversight, performance optimization, and long-term operational control. So that other layer that we needed to incorporate was the solar generation. Our energy model determined that approximately 89 kilowatts of solar capacity was required to achieve the city's level 3 net energy target. We ended up putting in our max that we could fit on our roofs, and we ended up providing 99 kilowatt capacity, exceeding the model requirement while maintaining the intended renewable energy offset. It's also important to note that the electric vehicle charging that is provided within the building were not included in the original energy model. The decision to maximize that rooftop solar capacity provides an additional on-site generation to help offset any of the future EV charging demand and support the city's long-term operational resilience. As part of our level 3 requirements to verify performance, it was not just we didn't just model that in the energy model. It was done also on site. So we completed a envelope commissioning and whole building air tightness testing. We tested the fenestration and enclosure interfaces to confirm proper installation and durability. Then we performed a blower door test on the entire building to validate the air barrier system performed as designed. That means the energy model assumptions around infiltration weren't theoretical, they were measured on site. It gives the city confidence that the building will actually perform the way it was designed to. So our whole building air tightness test was conducted at 75 pascals in accordance with the city's corporate green building standard requirements. The result presented reflect measured performance at that pressure. Testing confirmed that the living quarters performed tighter than the overall building. However, the project did not fully achieve the target that we had set. It came very close. Primary leakage contributors were identified to be at door interfaces and localized facade transitions. The measured values remain within the typical institutional performance ranges for a facility of this type. Targeted improvement measures that we enhanced on were additional weather stripping, especially at the sectional doors and aluminum doors, and at some localized detailing areas within the facade. So some of these were identified and can be implemented to further improve the envelope performance without impacting the current occupancy of the building.
Finally, the commissioning process is critical to ensure that building systems operate as designed. So it is increasingly important in higher performance buildings as newer systems and technologies can require finer tuning, to ensure their proper function. Through the commissioning authority, the city's monitoring-based commissioning requirements complement the fundamental commissioning provided by providing further oversight and verification to ensure that the building will meet its energy targets during building operation. So this includes the implementation of an energy management and information system, or an EMIS, that continuously tracks building energy use and operational data to identify anomalies, with the end goal of rectifying inefficiencies as they occur to help reduce energy use, GHG emissions, and ultimately utility costs over the life cycle of the building. All of our projects will undergo metering and monitoring-based commissioning to establish the actual operational baseline and to facilitate long-term management and retention of like-new EUI performance.
So thank you all for listening. This is the end of our presentation, and we will be taking questions. I see some questions have been coming in, and I've been keeping my eye on them. So I will read them out and I will direct them to who I think will be able to answer them best. Starting with, what was the design reason for the vertical garage doors over the horizontal? And does the climate, winter or extreme heat, impact these doors? And the person noted that this is the first building they've seen vertical doors on a fire station. So Sebastian, maybe you can answer this, and John, if you would like to jump in as well after.
Yeah, so with the Station 123, the fourfold doors at the front are there to maximize the speed to get out of the hall. The roll-up doors at the back, they're not rushing to get back into the station. So we were including those in the back as a cost measure, as the fourfold doors have a premium price to them. With the vertical doors, typically used to be at the front, but as the trucks would be coming out, they're trying to get out in a fast manner and typically would end up hitting the bottom of the doors. So there's been a big switch in using the fourfold doors at the front. John?
Yeah, sure. Thanks, Sebastian. So they are becoming much more common in fire stations for many of the reasons Sebastian mentioned. Speed is probably the driving factor, as well as they are designed to be a low maintenance door. They're very heavy hinges, low maintenance, low failure points. They should be a long lasting door, and well, let's be real, they look good too, right?
Yeah. For from a climate standpoint, the sectionals are high performance. They meet the same requirement as the building envelope, or close to. There are R20 for the back doors. The front doors, as you're seeing, they have fully glazed, so they can be able to see out. So the R value on those are much less than the back doors.
Great, thank you. The next question is, are there any safety concerns with not fully isolating sleeping areas? For example, when people are sleeping, people are still able to enter these spaces. I will start by answering this, and John, if you want to add to that. Ultimately, folks who are, the firefighters who are in the station need to be able to respond to a call even when they're sleeping. So getting out as fast as possible is very important, and that's why you will see there's a minimization of the amount of doors between someone sleeping and getting out. This is still a very vast improvement from that initial open dorm area that we've seen in the past. And the crew that is working on a truck, they are working together, so it's not necessarily strangers. So there is a requirement to balance privacy, safety, but as well as ultimately meeting the job goals. John, is there anything else you want to add to that?
Sure. I mean, I guess to directly answer the question, no, there's no safety concern. These crews do work very closely together. They trust their lives to each other's hands, and they all know where each other is at any time, because when they're responding, they have to respond as a crew together. No one gets left behind. So we did go with the semi-private dorms very intentionally. And another comment we've heard back is, with a closed door dorm, there is that potential for isolation. We want to make sure that our crews are able to communicate with each other and coordinate whatever they're going into, whether it be training or meals. So we believe that this is a good balance between full private and semi-private.
And to also add another layer to what John had noted, and Petra, for nighttime, there's also low-level lighting illuminating the path, so you're not disrupting anybody else's sleep, turning on above lighting in that corridor going into each dorm. So there is multiple controls within that dorm area not to disrupt anybody's sleeping.
Great, thank you. Who was the contractor / CM on the project, and what was the project timeline and cost?
So the contractor was Gaiman Malloy, and our project timeline was about 16 months, which we were able to achieve substantial performance 5 days earlier than the contract. So hats off to Gaiman Malloy for that. And our cost for this build, inclusive of all full electric, we're at $11 million.
Thank you, Sebastian. And maybe you can answer this next one. Why is the brick cladding suspending from the wall and not sitting on a foundation wall?
Yeah, so that tied back to the ferro bracket. So with the ferro bracket projecting the brick out, we're able to run the insulation from foundation to above grade wall continuous. That allowed the foundation wall to actually be much smaller than typical.
Thank you. What were the provisions for dealing with contaminated water from post-fire equipment cleaning?
It's a good question. John?
So I mean, I can start. So some of our purpose-built equipment does have filtration systems to catch sediment. The runoff, the separation of the sediment to the water goes to municipal, but the solid contaminants are trapped in the particulate filters in our washing equipment or extraction equipment.
Great, thank you. And what was the biggest challenge when implementing the net zero energy mandate from the city? Is there enough space for PV panels?
Yeah, so with that, there was a bit of a balance and back and forth during design of, as we were seeing, like the different design options for building envelope. We looked at different mechanical systems, how much loading was on the building. Our biggest load actually right now is the lighting, not even the mechanical plant. So the lighting is our biggest load in the building. And knowing how firefighters kind of operate, the lighting levels that we had to put into the energy modeling might actually be less in actual practice. But to meet the solar PV requirement and implementing that, we ran through different studies for on-site generation, flipping the building back and forth, trying to optimize as much of the roof area as possible without putting in solar PV structures out in the parking areas. So we were looking just to maximize every inch of that roof space, but minimizing, knowing how much we can maximize, minimizing that demand load as low as possible. So I think that was the biggest challenge, is figuring out our loading on the building and seeing how much we can actually optimize with our roof planes.
Thank you. And I don't see any further questions, so I'll give it over to you, Shalika.
Yes, I actually have a question. So let me just pull it up here. So I wondered if you could all clarify whether the projected EV charging loads fall within the surplus solar generation capacity, or would those loads exceed what the 99 kilowatt system is expected to offset?
So when we started, we ran through with the city's energy management team. We wanted to clarify and confirm that the targets provided in their manual is for the building, which was confirmed. So our building, as a standalone, meets the net zero energy requirements. We've added in extra solar PV to accommodate future EV charging, because there'll be 2 fire trucks in the station. At the time, I think John and his team were still going through determining what truck and which system will be utilized. So we weren't able to accommodate for it. But hopefully, with the lighting levels not being used as much as we were expecting, hopefully that will help offset the EV truck charging.
Just to expand that a little bit, when we were designing the station, trying to determine what the EV loads would be for a fire apparatus, there was no EV fire apparatus that was market ready. So we didn't have the information from the manufacturer. That's step 1. Step 2 is we didn't have a fire truck in practice to know what the charge cycles would be, what the demand would be, to be able to properly or adequately estimate what that gap would be. The EV chargers on the level 2 is on the staff side. Same thing. We don't know what the adoption is going to be with staff to know what the loads are going to be or the charge demand. So we have the capacity there. We don't know yet what the demand will be.
Actually, I see a follow-up question to the foundation. So is there a reason, Sebastian, we didn't go with a 2-layer foundation with insulation in between?
Yes. So with that one, we've proposed that type of an assembly below grade. If you're looking at doing a full insulation line into walls of concrete effectively, some GCs don't like it. They find it to be difficult to actually do on site. And we've done other foundation walls where we have the first 2 or 3 feet, or sorry, 4 feet of insulation in between, and then the exterior insulation on the outside. And I found once they actually do that installation on site, the insulation and walls are not as straight, and you're not getting the same R value as you wanted with what we were looking at doing here as an R15. Your assembly would be actually a little bit bigger than what you are looking to install.
That and carbon, right? We wanted to, if we didn't need to use the extra concrete, then we didn't want to put in extra concrete.
Yeah, the concrete, the foundations just get bigger when you're trying to carry the load of the brick.
And is there any PV battery storage?
Not at the station, no. And that would be another item when cost implications come into effect.
And was a geothermal/electric hybrid option discussed when determining mechanical systems? And if yes, how did it compare to all electric?
Geothermal was discussed early on, and it didn't gain traction mostly because of budget. So geothermal was a very cost prohibitive approach for what we were looking to achieve on this build.
Great, thank you. So I don't see any further questions, Shalika. Not sure should we wrap it up?
We can. I mean, there's still, sometimes. So if anyone still has any last minute questions and you're typing them in the chat, please continue to do so. I can get started with maybe some of our closing messages, and then if there's more questions, feel free to
Absolutely.
continue to answer them. But I will begin by just giving a big thank you to our speakers today. Thank you, Petra, Sebastian, Paul, and John for this really excellent presentation. I know I learned a lot about fire stations that I didn't know before, so I hope our attendees did as well, that they took away some really important information. And we've had a few comments already just saying that from our attendees saying how much they appreciated the presentation as well. And of course, thanks to everyone who attended today and who submitted your questions for our speakers. As we conclude the webinar, again, I just have a few announcements to draw your attention to. So for those who are seeking continuing education learning hours, the OAA will record your participation in this webinar on your OAA transcript. So there is no need for individual reporting on your part. We just kindly ask for your patience at this busy time of year as we process and confirm the accreditation of your hours within the next few weeks. All attendees will be, I believe, receiving a PDF copy of the presentation, but you will also be receiving a link to the survey to submit your feedback for our webinar and our presenters, which we all highly value. So if you do get a minute, please do complete that survey. Our next webinar is also going to be another climate action webinar, and this one will take place on Wednesday, March 25th, with the title Innovation in Repeatable Low-Rise Housing. So keep an eye out for that one and sign up if you are in need of your climate action hours. And if you are looking for additional ways to get your Con Ed hours before the end of cycle, which again is in June, be sure to check out our Con Ed opportunities page, which is on the OAA website, where we list education opportunities that are offered by other organizations beyond the OAA. So that's another great way to find some Con Ed. And finally, on our end, if you would like to contribute to the OAA's Con Ed program as a webinar presenter, our CFP for the fall and winter sessions is now open, and you can find the CFP on the OAA's website. So please check it out and submit your ideas before March 6th. And before I give my last sort of thank you, I think we did get one more question. Yeah, I got a few more questions. So feel free to jump on.
So there's a great one, and it was actually one that we've had a lot of internal discussions, and even us while preparing for this presentation, we had some great discussions about this one. And it is there feedback from this project solution back to the standards it was based upon? And I think the answer is yes. And maybe Sebastian, you can start.
No, I would like to. I'd leave that one to John and Paul.
Okay.
Because
I can.
We're able to work with the standards. It's very straightforward, but from a practice standpoint and user operation, I think Paul and John would probably be best suited for that.
Yeah, I can start, John, and then pass it over to you if you like. So internally within our capital design and construction team, we've got a large group of project managers that are working on various fire projects. As John referenced earlier, there's a large volume of work with Mississauga Fire and Emergency Services, be it renovations, be it brand new builds. So we do have quite a few of my colleagues that are becoming quite experts, if you will, on these types of projects, and they're kind of refining their skills on every one of these projects that we do. Because we're talking about, in some instances, like cutting edge technologies and things that are changing relatively quickly, it's a great question, because I think we certainly have groups within our unit, within our capital design team, that do meet on a regular basis. They exchange lessons learned. They exchange feedback on how the designs are evolving on their various projects. And each of these kind of inform the next project, and we're kind of refining ourselves as we go along. And we do bring that back to John and his team as well for discussions, and ultimately what might lead to, which would lead to revisions to the design standards. Let's call it a 2.0 or eventually a 3.0. You know, these standards aren't stagnant; they're intended to be refined and evolve as we go through different projects, and we push the envelope on our sustainability targets. And John and his team kind of bring new sort of design principles forward to us. So I think it's to Petra's point, we are constantly looking at these things, and if the end goal is really to have as up to date a refined set of standards as we can as we move on from stations to stations.
Yeah, Paul, thank you. And the question is absolutely yes. We've learned so much on this station and the previous ones. The race is really, because we're building and renovating so much, is trying to take the lessons learned and apply them before you go to that point of no return. So we've learned a lot from Station 125 net zero energy as well that we applied here, and we've learned a lot here that we're applying to renovations and new builds. And all of our project managers on the capital design and construction team are working together. And I mean, there's late night emails. Hey, we've just installed this at this station. Please make this our standard going forward. So without question, having a set of a document that we can reference that's constantly evolving provides so much efficiencies and opportunities to just benefit one project after another. So yeah, 100%.
Yeah, a big one, I think, was like during the middle of the project, there were other slight revision from an electrical standpoint and PA systems, and how from an operation standpoint, things can modify in your end, John, that to be implemented right on the fly.
Yeah, and one of the things I think one of my favorite features about this station is the access to the change room, which is our shower decon area, the primary one off the apparatus bay. There's a direct access off the apparatus bay where you do not have to enter the living quarters first. So this is the first station that we applied that in. It's a very simple design change, but probably one of the most impactful one in protecting our firefighters. Being able to get direct access, you can see there that direct access from bay is, again, super simple, but incredibly brilliant, and it works really, really well.
Yeah, and that involved just our conversation going through that sequence that we went through earlier in the presentation and kind of walking through what is going to be the day-to-day at this hall, and then that door kind of comes up of that needs to be here in order to maintain that kind of separation there.
And we learned to give firefighters as little options as possible. Give them one point of entry and exit, and they'll follow it. If you give them an alternate choice, they're probably going to follow the alternate. So minimizing that through deliberate signage and paths, it's very effective.
And how many other new stations are under construction or in planning / RFP stage?
So there's one station in addition to this one that's in construction, and then there's 2 more new builds that are not yet started, that are in the planning phase.
Great.
Paul, and there's a bunch of renovations as well, but as
yeah,
far as new
there's a lot of renovations as well. That's right.
And do the standards or process allow for exceptions to the standards for extenuating circumstances? And I'm assuming this is a question regarding new builds, because I know on renovations, yes, there would be exceptions.
I think it's fair to say, yeah, I think it's with regards to the sustainability aspect, I think there, for certain, there would be site-specific conditions, building footprint, et cetera, that can mean different solutions. So if that's, I think if this question might be leaning more towards the design standards, John, and the actual, and I think there has to be flexibility. Again, when you look at the footprint of this building, it's not, it's not a typical rectangular building. You really, the DPAI team really had to adapt to a site that had a bit of a wedge shape to it, and it translates into the floor plan, the site plan look. So you did definitely had to massage things. So it's the first principles that we talked about earlier that get maintained, and then things have to be massaged accordingly based on site-specific constraints.
Because the standards do provide for a floor plan layout, but that was just to explain some of those first principles. The understanding is the first principles need to be applied on every new fire station. The floor plan was there just to demonstrate, just an example.
Yeah. The standards themselves don't change. How they're applied and how they integrate into the unique property or land is going to vary. We're a fully built out city, so the idea of buying a perfectly square rectangle property is not a thing. So this unique shaped property provided a great opportunity to be very innovative, and I think it's a great result.
And speaking as an architect, no architect wants to see a set of standards that tells them how to design a building, but it does make it easier to understand what the constraints and the objectives are, so that you can really focus on designing a building with those in mind. Okay, I don't see any other questions.
Yes, thank you for all of those who input your last minute questions there for our presenters. I think those are some great ones to end off on. I just want to quickly read, as I said, we've have a lot of really positive feedback, more comments rather than questions in the Q&A there as well. So just want to read a few of them. We had someone who said, great presentation, very insightful, and learned a lot about the importance of fire station design. Great to see a push towards integrating functionality and sustainability. Well done. So positive feedback there. Others who have said, again, it was just very comprehensive, a very thorough, clear, concise presentation. So some great feedback from our attendees for all of you. So thank you once again to all of our presenters, and thank you for our attendees who participated and who stayed until the very end of this presentation. Again, we gave our announcements already, but for those who are seeking the continuing education hours, we will be inputting those hours for you. So just a reminder about that. And I guess with that, I will leave it all. So thank you once again, everyone, for your attendance, and have a pleasant remainder of your day. Thanks very much.
Thank you, everyone.
Thank you, everyone.